Okay, so welcome, ladies and gentlemen. Bienvenue, mesdames et messieurs, because we are in Montreal, so I can speak French. So we are super happy. The IIF is extremely happy to have our ISF today, the 46th ISF in Montreal. This is not the first time that we come to Montreal, but the last time was in the previous century, I think. So I cannot think about a better city for an international institution than Montreal. So we are extremely happy to have you there. Let me start by thanking the organizers. So we have Dalibor Stevanovic, the general chair. Thanks a lot, Dalibor, for the huge work that you did. Thanks a lot to the program chair. So we have Alain Gay and Philippe Goulet-Colombe. And also I would like to thank the true organizers, Lina. Thanks a lot, Lina, for the organization. You're really the pillar of this conference. And I would like also to thank Ying. Maybe you know Ying Fry. Ying is our business manager. So Ying is really the pillar of our institute. So thanks a lot, Ying, for the work that you do. So I'm not going to be long. I just want to recall you a few things. First, we have a fantastic lineup of academic speakers. So a few of them are here already. So that's really, really fantastic. I'm really happy with that. So we have also a track of practitioners. You know, the Institute has the specificity that it's not a pure academic institution, but we are a mix of academics and practitioners. So our aim is to bridge the gap between the two. So, and this is what we try to do. So you will see a lot of famous academics in the room, and you will see also young guys working in startups with AI tools that maybe you never heard. So it's going to be super, super interesting. So thanks a lot, Dalibor, again, for putting this fantastic conference. We have if you remember the old time, we had a book with a program. So it's over now. We have this app, which is called Whoa, much more convenient. So you have all the program on Whoa. So have a look, please. Just remind me, I would like to remind that normal sessions are about 20 minutes. It's talk about 20 minutes. So think about having a speech of 18 minutes and save maybe 1 or 2 minutes for question if you can. Most of the time, the chair of the session will be the last speaker. So the chair has strong incentive to respect the timing, okay? Also, you will see that some sessions have students' presentation, and we give prizes to the students. So you have the possibility to give a grade, okay, with the app, with the WUA app to a student presentation. So if you are a student, please announce in advance, I'm a student. No, I'm not a student, but if you are a student, please say that. And so that we can not forget to give you a grade for your presentation. Okay, let me stop here. We have now, I think, a video with the rector, okay?
Yeah. So
thank
you, Laurent. So yeah, the president of the university was not able to come this morning, but he registered a video, a welcoming video. So now we're gonna show that.
Bonjour à toutes et tous, bienvenue à l'Université du Québec à Montréal. It's a real pleasure to welcome you to UQAM, the University of Quebec in Montreal. Our university is very pleased and honored to host the 46th International Symposium on Forecasting. I want to acknowledge the outstanding work of the organizing team from our School of Management, beginning with Dalibor Stevanovic, General Chair of ISF 2026, and Alain Gay and Philippe Goulet-Colombe, Program Chairs. Thank you as well to all colleagues, staff members, and partners who have made this conference possible. Forecasting is not only a technical exercise, it is a tool for helping societies, institutions, governments, and organizations make better decisions under uncertainty. And uncertainty, as we all know, is not in short supply. We are living in a period marked by inflation, geopolitical tensions, climate change, energy transitions, supply chain disruptions, and rapid advances in artificial intelligence. In such a context, the ability to anticipate, to test assumptions, to assess risks, and to communicate uncertainty is clearly essential. Forecasting does not eliminate uncertainty, but it helps us face it with more rigor, more humility, and better tools. This is one of the reasons why UQAM is proud to host this symposium. Our university has a strong tradition in economics, quantitative methods, data analysis, and applied research. I would like to underline the important contribution of our chair in macroeconomics and forecasting at ESG UQAM. The chair brings together academic expertise and the concrete needs of economic institutions in Quebec and Canada. It is a strong example of how research can inform public debate, public policy, financial decision-making, and economic resilience. In a time when economic signals are often complex, unstable, and sometimes contradictory, this kind of expertise is not a luxury. It is a public good. The program of this symposium brings together leading voices in forecasting, research, and practice. It shows that forecasting now cuts across disciplines, sectors, and institutions. We are especially pleased to begin this program with Professor Mark Watson of Princeton University. His work is well known to the forecasting and macroeconomics community, and his presence here is a privilege for all of us. I wish you all productive discussions, a stimulating and inspiring symposium, and many opportunities to build new collaborations. I also hope you will have the chance and the time to enjoy Montreal, especially the Latin Quarter where UQAM is proud to be rooted. Welcome to UQAM, welcome to Montreal, and have an excellent ISF 2026.
Well, thank you, Stefan. In fact, he probably wrote his speech. He's an economist. So he hired me back then. He was a chair of department and a colleague of Alain. He already introduced Mark. So I will just say that, we don't need to introduce really Mark Watson, especially in this crowd. So everyone is aware of his great contribution to the field of forecasting, but also to the general field of econometrics and applied macro. So we are very happy to have Mark starting this conference as a keynote. Mark, the floor is yours.
I'm going to move just for 1 second so I can see you guys. Okay, so that's who I am, and that's where I'm from. So it's a great privilege and honor and stuff to be here. This conference is always great. Montreal is always great, and if you put them together in June, you've got you're in heaven. This lecture I looked is it's the Arnold Zellner Memorial Keynote Address, and I think it makes sense for those of us that all of us know Arnold, of course, in his work, and many of us knew him personally. He was a wonderful, dedicated academic. We know his contributions to, obviously Bayesian econometrics and forecasting and time series and everything else. I remember vividly the first time he invited me to give a talk in his seminar at Chicago, and I was, sort of a young kid, and he not only invited me, but had read all of my papers, all 4 of them, before I got there, and was anxious to talk about them. I remember, I think what stands out or illustrates Arnold for me was not all the work he did when he was at Chicago, but after he retired. Okay, so people, when they retire, they take up golf, right? And Arnold took up golf. And, you know, that was his first paper, right, after he retired, right? I mean, it's perfect, right? Some issues that arise are, is there a scientific analysis of golf? What concept of probability models and inferences are most useful, et cetera, right? But it's something, you know, for those of us who think maybe we will retire at some point in our lives, right? You know, this is exactly the kind of thing that you know, Arnold leads the way here too. Okay, so with that out of the way, you know, I'm going to talk about the topic of this lecture, which is forecasting the COVID recession, the COVID inflation. So here's the story. So here's inflation. You guys, I'm sorry, and this is for the U.S. Okay, so all of the data we're going to look at today are for the U.S. I'm going to talk about some models that may be relevant in other countries, but I'm going to do the U.S. Okay, so this is. You know, so you can see, so here's the history of inflation going back to about 1960. Here's the period I'm going to be interested in. You know, in particular, think about COVID starting, you know, in the first quarter of 2020, right? Inflation dipped down. That was primarily, or a large part of that was energy, right? And then started picking up in early 2021, right? And there was this COVID surge, right? And now, and it had come down to around 3% before the latest energy shocks. Okay, so here's another, for those of you that, you know, are sort of interested in policy, here's another picture which is kind of telling. Here's the surge in inflation, right? And here's the policy rate, right, in the United States. Okay, so interest rates in the United States, you know, started moving, I'm probably going to get the date wrong, something like March 2022. Okay, so it was after, right, this big surge, and then it increased slowly, and then, right, sort of very quickly. So the question is why were policymakers so slow, right, in reacting to inflation, right? And you know, and there are sort of two reasons that come to mind, right? One reason is, of course, you know, what policy was trying to do here was to support real economic activity as we were recovering, right, from the COVID recession. And here's a picture that I think is just stunning. This is from, I think Jim Stock did this in this paper. And, you know, it shows peak to peak trend rates and real GDP, right, for each of the recessions since 1960. And you see, well, you see the trend rate has fallen, right? But one thing you see in particular is, you know, in all of the recessions before this one, we really never returned to the trend rate of growth, right? Or to the trend, right? But we were successful, right, in doing that, right, in this final recession. So you can think about, if you want to think about economic policy generally, right, was, at least in the U.S., right, by this measure, right, was quite successful, right, during this period. Okay, and that, you know, that's part of the reason, you know, this gets some credit for that. Okay, so supporting economic activity was one thing, but, you know, another thing was that, you know, we all lived through this period, right? And this inflation surge was forecasted to be temporary. And this is a remarkable picture. You see a version of this picture in several different papers, right? I stole this from many of them. And this is what you see. So here's inflation that we saw before, right? And here are the SPF forecast trajectories, right, at each of those dates. And what do you see? Well, you know, the Fed thought all this stuff was going to be temporary, right? And sure enough, right, the professional forecasters, the median professional forecaster here, right, also thought this inflation surge would be temporary. Right, here's the Fed's, this is from the Survey of Economic Projections from the Fed. These are the forecasts that the Fed was, sort of the dot plot forecast that the Fed was produced, right, in December. This would have been December in the year before 2020, so this was December 1919. They thought inflation would be about 1.9%. It came in at 1.2. In 2021, so this was a forecast they made in December of 2020. They thought it would be 1.8. It came in at 5.6. You know, this is kind of a quite interesting one. This is December of 2021. This is December of 2021, right? Inflation was quite high. They predicted over 2022 inflation would come in at 2.6. Again, consistent, right, with these professional forecasters, when in fact, right, inflation came in at 5.8. So this was, you know, I guess it's kind of awkward to start a forecasting conference with, you know, one of our greatest failures. But this is right up there with one of our greatest forecasting failures. Okay, so what did I think, you know, I would do here in this is try and deconstruct this forecast failure, right? And see, you know, what were the causes, you know, could we have done better, et cetera. I'm going to do this in a really particularly simple way. I'm going to write down or analyze two very simple forecasting rules, right? One of them is going to be a univariate forecast of inflation. The other is going to be a multivariate forecast of inflation, but it's going to use only inflation data. So these are going to be very simple time series models. And I'm going to see from those, did those models predict this? The answer is yes and no. It's a good thing for all talks, yes and no, right? And particularly when they're no, right, why? Right, what were we learning along the way, right? And for yes, what was the additional information, right, that was used? Okay, so that's where we're going, right, in this thing. There's like a literature on this, and I'm terrible at like listing all the papers. So I wrote a little paper as I was preparing these slides, and you can download this paper, and there's a bunch of references there, right? So I'm not going to talk about this. I will talk. Our chair has a paper. Dalibor has a paper on this, so I'll mention his work, okay? But aside from that, everyone else here I'm going to ignore, okay? Okay, so here's a version of the simple model I'm going to use. Okay, so it's so it's like a Harvey local level model, unobserved components model, right? Simplest model in the world, right? Inflation has a persistent component, you know, let's call that tau, and a transitory component, right? Let's call that epsilon. Persistent component, let's model it as a random walk. Transitory component, let's model it as a white noise. Okay, so this is, right, everything's Gaussian here. Okay, what's useful about this model, or what's kind of a feature of this model, of course, is that if I think about predicting future inflation, right, you're going to predict the future value of tau and the future value of epsilon. Epsilon's white noise, so its expected future value is 0. Tau's a random walk, so its expected future value, right, is its value today, or your best guess of what its value is today, right? So this estimate of tau based on inflation up through time t, right, tau tt, right, is going to be a scalar summary, right, of forecasts in the future. So if we sort of track this, we can think about, right, what forecasts are going to be, right, going forward. Right, another representation of this model, and it goes, you know, you guys know this, but I'm just going to get some notation here, right, is, you know, this model, of course, is an ARIMA 011 if you were, you know, in Box-Jenkins land, right? So, you know, think about the first difference, of inflation. What's it going to be? It's going to be the first difference of tau. That's this white noise bit, and the first difference of this white noise bit, right? That's going to, introduce a negative moving average component, right, with the coefficient theta, right? Theta is going to be between 0 and 1. It's going to depend on the variance of the permanent component relative to the variance of the transitory component. If the variance of the permanent component's big, theta is going to be close to 0. If the variance of the transitory component is big relative to that, theta is going to be close to 1. Okay? So we can think about theta, right? This is this sort of, if you will, signal-to-noise ratio or something like that, right? The variance of the permanent component relative to the transitory component. We can think about, theta as sort of a scalar summary of persistence, right? That's going to be important over this period because this theta is going to change, right? The shocks were more persistent, right, than we saw, right? So we're going to think about theta coming into this episode and theta going out of this episode, right? How quickly did we learn, right, that the relative variances of these guys were changing? Okay? Oh yeah, well, okay, so here's just a little, connection. Obviously, if you're predicting, inflation, K periods ahead, right, using this, of course, it's going to be this tau TT thing. Here's a simple little formula for it, right? So if theta is very close to 0, that is if the permanent component's big, right, you're going to put a lot of weight on current inflation, right? If the transitory component has a variance which is big relative to the permanent component, this theta is going to be close to 1, right, and you're going to be averaging inflation, right, going back in time. Okay, so let's go back to, here's the time series, right, that we're looking at, right? It turns out this little simple model I wrote, right, doesn't quite fit these data well, right? If you look at this, there are periods of time when inflation went up and then came down, right? So that's the permanent component kind of took off, right? Its variance got big, right, for a while, and then there are big periods of time in which inflation's relatively stable, so the permanent component, right, has a small variance, right, and then there's this period at the end, of course, where inflation took off again, so its permanent component went up. So what do we want? Well, we want some time-varying variances in this thing, some stochastic volatility, right, so we'll add that, right, and occasionally, right, as I wrote this model, right, it had Gaussian innovations, right, if you look at some of these jumps here, right, they don't look very Gaussian, right, so you want to throw in some outliers, right? So, a standard model for this, right, is to kind of soup this thing up a little bit in a couple of different ways, right? One thing, you're going to do is, allow these two components, the permanent component and the transitory component, to have variances that evolve through time, right? So you can do that, in a straightforward way, right? The way I'm going to do it here is sort of a standard method that's been used, for a while, which is just, to let the logarithm of these standard deviations or variances evolve as random walks, okay? And they're going to evolve as random walks. It's going to be important. We'll come back to this in a little bit. They're going to evolve as random walks. A standard model for these is that these innovations are going to be Gaussian, right? That's going to be great. That's fine for sort of fitting these data, but in periods of time in which these volatilities change very abruptly, like they did in early 2021, turns out when we look at the results from this model, this Gaussian model isn't going to be particularly good, right? We may want to do something else there, okay? The other thing you might want to do is to put in outliers, right? And you can put in outliers by, instead of having a Gaussian thing, having a Gaussian mixture, right? And that's what this has done. This is kind of a very crude way of doing it. In this model, a version of which Jim Stock and I did many years ago, right? We use this very crude mixture, but there are better ways to do this, and you can see the references, right, in the paper that I outlined, right? So this is usually, S is equal to 1, everything's fine, and then occasionally S is really big, right? Allowing for outliers here. Okay, I'm going to cheat here in a variety of ways, or cheat or change things. One thing I'm going to do is I'm going to get rid of energy, okay, because forecasting that is difficult. So let's get rid of the energy component, right? Often you get rid of energy in food. Sort of a pet peeve of mine for a long time has been, why are we getting rid of food? I mean, back in the 1970s, right, food was very volatile, like energy, and hard to predict. And so we started using core measures, which were X food and energy. But post-1970, food became more predictable, and it doesn't behave like energy. So I would suggest that we should use, X energy core inflation instead of X food and energy. So that's what I'm going to use here. I plotted all of them here, right? What do you see here? Well, a bunch of the big dip in early in the recession was energy, right? If you get rid of food and energy, that comes down a lot. It turns out food prices went up instead of down, right? So if you include those, right, you do a little better, right? This is the Ukraine war up here, right? That energy prices were just higher than core prices. So I'm going to be using X food and energy right in the rest of this talk. Okay, so here are these data over this critical period. I'm going to be focusing on kind of what happened right here. Okay, so these numbers are important, right? So in 2020, coming out of 2020, I'm going to use quarterly data. I probably should be using monthly data, but monthly data is always harder for me than quarterly data. The little bit of smoothing, right, that you get with quarterly data turns out to be helpful, right, for smoothing some things out. So that's what I'm going to use. Okay, and someone should do this right with monthly data. Okay, so in the first quarter of 2021, right, inflation popped up to about 3.2%, right? Then by 2021 Q2, right, inflation jumped up to about 5.5%. Okay, and then blah blah blah. Then it kind of continued here, and I'm not showing you. What happened when it came down, okay? So the question is, right, this kind of went up here, right? When did we notice this, right? So that's going to be the question that I'm going to focus on. Okay, so remember this tau T thing, right, was sort of an indicator, right, or a sufficient statistic, I guess, if you will, here, right, for forecasts of the future. Right? One thing you might do is, take this little model and estimate it, right? And then ask, how did tau evolve? What does the model say about how tau evolved, right, over this period? Okay? So what you might do is use all of the data, right, to estimate how tau evolved, right? That's not a forecast, right? That's just sort of fitting this thing, right? But what do you see here? You see, the model kind of viewed tau as an important contributor to the variance, right, of this series, right? So sure enough, ex post, right, tau is very close to the inflation rate. So if you had this tau T, capital T thing, right, at your disposal early on, right, you would have predicted, right, this increase in inflation, right away. Okay? Now, this, of course, is cheating because this is using data after the fact, right? So let's look for this model, right? Let's look at what happens if you look at, the filtered value, tau T, little t, right? And what does that look like? Oh, no. I guess I'm not going to do that, right? Sometimes when you prepare slides in advance, like a week in advance, you kind of forget what's up here. Right? Okay, so I'm reminded what's up here. So these are these parameter values, okay? In this, right, we've got stochastic volatility going on here, right? So there's, right, there's the variance of this permanent component, or random walk component. There's the variance of this white noise component, right? And then there's this moving average term, right, which is, you know, a function of these things, okay? So this is what the model says ex post, right? This is what the model says how these guys evolved, okay? So this is kind of interesting, right? So from 2000, right, until, well, the beginning of the recession, right, this was kind of stable. It looks like in the recession of, you know, 2008, the volatility of inflation kind of popped up, but this is this transitory bit, right? And then what happened, right, when we went coming out of COVID, right, the variance of this permanent component increased a lot, right? And the variance of this epsilon component, right, didn't move. What that meant is that this moving average coefficient, right, moved from being a number like around 0.6 or 0.7, right, down to a number that was around 0.1, right? So you're putting a lot of weight on past inflation if you're forecasting. Right here, you're putting very little weight on past inflation, right? That's consistent, right, with this picture, okay? Okay. So now, okay, so that's kind of what the model says the evolution of this. Now here's one thing that's weird, okay, or a problem, right, with this model, right? If you look at the data, it looked like, you know, inflation kind of took off. This sigma tau thing, you know, kind of was nice and stable, and then it increased, right? What does this model say? Well, this model says, well, actually, it was high not only in 2021, but, you know, it was high in 2019, right? Why is that? Because there's a bunch of smoothing going on here, right? And this has a Gaussian evolution, right? So what it's going to do, it's going to sort of smooth all of that out, right? So this is an indicator, right, that you could do a little better with the specification of the stochastic volatility term, right? That's kind of clear from this. Okay, so now what do I want to do? I want to move, right, this was a two-sided thing. Let's move to a one-sided thing, if I can. Yeah, okay, so here's the one-sided thing. Okay, so this is amazing. Two-sided thing, you knew inflation was going to take off. Well, what if I only use the data on one side? Well, you know, I don't know, it's sort of the same, right? Maybe, I don't know, maybe you're like a quarter late or something like here, using the one-sided data instead of the two-sided data. So when I first looked at this, I thought, God, these professional forecasters, some of you in this room, you know, are really bozos, right? I mean, I'm sorry, I don't mean to insult you, but gee, this little simple model just nails this, and if we were only using these sort of simple models, we would have kind of gotten this, and so there, right? Why were you guys so late? And then I thought, well, it turns out when I computed this thing, I cheated. I was lazy, okay? How was I lazy? I used these parameter values, okay? I used those parameter values, and then the data, right, to the left of the data, right, with these parameter values, and sure enough, right, that's what I got. That is, I told the model, right, that the variance of the permanent component, right, had increased. That's what this slide says, right? This was my cheat. I used the full sample parameter values, okay? What do you want to do? Well, you want to use, of course, the parameter values that you might have computed, right, using the data up through time t, right, which is, you know, obviously this thing, right? I called this thing, right? But that was my cheat. Okay? That's what this says, I cheated. Okay. So sure enough, what if you don't cheat? right? Well, then the picture gets much cooler, right? It looks much more interesting, right? This is what it looks like. I like this, right? This is this sigma tau, sigma epsilon, theta thing. Here's the theta thing. This is great, right? Here's the theta thing. It says, in real time, if you were following this is what you would have thought. Going into this recession, you would have thought you should be using a theta, with a coefficient value of around 0.8, right? Inflation's pretty much white noisy, right? It's not very persistent at all, right? Nice and stable around 2% or actually less than 2% coming into this recession, right? And then what happened is we learned we had a bunch of the variance of these permanent shocks went up, right? And then we want to use a model that's not, right, very white noisy. We want to use a model that's very random walky, right? So this theta, right, pops down, right, to about 0.2. Now, Delabar has a great paper on this, right? He considers forecasting inflation, right, using some simple time series models of this genre. In part of his paper, he's got a variety of things going on in his paper, but in part of his paper, he's got this going on. And then he asks, what happens if we were trying to forecast inflation during COVID and we were using the kind of model that we would have estimated in the 1970s? Well, the model that you would have estimated in the 1970s, right, would have had, right, a very small moving average coefficient. So sure enough, right, that's sort of using parameter values, right, that we were only learning, right, coming into this. Okay? So what happens, right, if you do this, right? Well, if you do this, right, what do you see? Well, now, right, you see it took a while, right, to learn that that the variances had changed, right, that these shocks were more persistent, right, than we thought. And then, instead of seeing this, in the second quarter of 2021, right, when do we see it? Well, we see it in the third quarter of 2021, right? So this learning about the parameters costs you can see the dots there, right? Boom, that dot's a lot lower than that dot. This dot, right, is much lower than that dot, right? So that's the cost of sort of adapting, right, of learning about these parameter values. Looking at Dean over there, and he's going, you still cheated, right? I hate this guy, okay? Because he always says this, right? He says, well, but you use, because again, I'm lazy, right? I just downloaded these data from Fred and then just did it, right? And he says that those data are revised and that matters, right? And I say, no, it never matters. And he says, yes, it does. And it turns out he's always right and I'm always wrong. Okay? So what happens if you use the revised data here? Well, here's the revised data. And there's a couple of interesting things going on here in the revised data. Okay? That obviously this isn't a methodological paper. It's just let's dive into these data and look at the particular little dots, right, that we're seeing one at a time. Okay, so what goes on in these data? There's a couple of things, right? There's this period right here, right, where, well, you're under forecasting inflation, you're over forecasting inflation in real time. Back here, I don't have this number. You also have this number right here. So you kind of are messed up here, okay? And I'll come back to these revisions right here, where they came from, and how they screwed things up, okay? But think about here, there's some higher volatility, right? Higher volatility revision errors here that are going to be important, right? And then there's all of this stuff right up here at the end, right? This turns out to be, financial services getting revised, right? That's not particularly important. This area, this period down here is much more interesting. Okay, so now let's do this right? Let's use these real-time data in this, right? And what happens, this is a very busy slide. Okay, I should pause here because you all certainly want to read every number, right? And look at every picture right on this slide. But what do you see here, right? Let's go back up. Let's go here. This is this moving average coefficient, right? This is important, right? This is what the smoother said, right? It smooths everything out, right? If you look at the revised data, again, it was like 0.8, it jumped down to 0.2, right? If you look at the real-time data, it was also sort of 0.8, it jumps down to 0.2, right? But it does so a quarter later, right? So using these revised data, it took an extra quarter, right, to see that you should be adapting. Now, why? Well, a little bit, you were a little slower, right, with the increase in, the variance of tau, the permanent component, right? But also, you got a little confused by this white noise component. You thought its variance went up. Why did you think its variance went up? Because that red thing, right, is moving around a lot, right? It turns out this volatility right here early on was important. I'll come back to this. We know what this is, right? This was, okay, you guys haven't thought about this for a while. I thought about it last week. This is like motor vehicles and parts, right? It was going crazy during this period. And that's what this stuff is all about, okay? So we'll try and capture that in a multivariate model, right, in just a minute. Okay, so there you have it. So what do you have here? This is kind of interesting. Okay, so here's the real-time numbers, where if you're doing this univariate model in real time, what would you think? Well, coming out of 2020, you're forecasting, right, inflation's going to be at 1.6, 1.7, 1.8, right, 2.6. Now, I want to be careful here. This is the data through 2021 Q3. The data from 2021 Q3 was published, available, right? This is the first release, right, at the end of October, right, in 2021, right? So really, at the end of 2021, right, what do we sort of know? Well, we're seeing sort of that number, right? Going back to what the Fed was predicting, right, in December of 2021, wasn't a whole heck of a lot different than that, right? Here's the estimate of tau that comes from this data through 2021 Q4. Again, when are you going to know about that? You're going to know about that at the end of January 2021. Well, then you're starting to see this pickup, right, in inflation, right? And this is when, the Fed started moving. So this little time series model has sort of captured, I think, what a lot of people were saying about inflation. And why did they get it wrong, right? Well, according to this model, they got it wrong because they didn't realize these shocks were persistent. They got the variance wrong, right? And they were using lousy data, or there was uncertainty, right, about what the actual inflation was. Okay, so that's kind of, I should pause here and say, okay, so that's, what does this say? Oh, look, okay, I'm sorry, I have this slide here that's supposed to summarize things, okay? Notice I used colors here, okay, to help me think through this. Okay. What does it say? I don't know, I'm supposed to, all of these colors are supposed to remind me of something, and then I'm supposed to say something, okay? So let's start with pink. Okay, that's when the inflation surge started, way back there. Inflation, real-time data, what does this say? I don't know what this shouldn't say. This is the real-time data. Yeah, okay, cost you a quarter. Okay, it started going up a quarter later. If you knew the parameter values, you would have gotten this. This is data after the second quarter of 2021. Again, you're going to notice that in July of 2021. right? And then there's confusion about the parameter values, right? And the preliminary data kind of pushes you up to here, right? So that's the challenge here. Okay, so now I'm going to go to multivariate models. Okay, so so multivariate models are useful for two things, right? There's an enormous literature now on trying to explain why the inflation surge happened. Was it supply shocks? Was it fiscal policy, the enormous fiscal policy we had? Was it the slow reaction of the Fed? You know, how much of it was energy prices associated with the Ukraine war, et cetera? You know, how much of it was pent-up demand, et cetera, right? Multivariate models are the key to thinking about that. My sense of that literature is that, you know, I don't think there's a consensus yet about how much of it comes from this factor and this factor and this factor. Okay? So I'm not gonna say this is really an interesting thing, but this was too hard for me. I didn't think I could make any progress on that above and beyond what people have done already. So what I'm going to do is I'm going to just look at a version of this model that looks at sectoral inflation and asked it, would sectoral inflation have helped us right through this? Okay? So I'm going to look at the same model and add sectors. Okay? So this is going to be a familiar model. It's going to look at, it's got, if you think about PCE, you can break it in crudely. You can break it into 17 sectors. PCE is personal consumption expenditures, so you could break the inflation into 17 sectors. 2 of them are energy. I'm going to throw those out because I'm looking at X-energy inflation. That leaves 15, right? So you've got some goods things. Now notice you can see like motor vehicles and parts, right? That's going to go crazy, right, during this, right? So you could see that it's going crazy, right? You know, you've got, you know, food and beverages. This is food at home, right? You've got food services and accommodations. This is, you know, hotels and restaurants and stuff like that, right? So you've got things kind of broken down here. And then what am I going to do? I'm going to estimate, I'm going to think about a model, right, which has the same structure as this little univariate model, right? So each of these little sectors, right, is going to follow, right, one of those little univariate, right, trend plus white noise models, okay? But, you know, some of this trend is going to be common to these different sectors, right? And some of this trend is going to be idiosyncratic. Some of the white noise bit or the transitory bit's going to be common. Some is going to be white noise. So the, you know, tau C is common, tau I is unique, right, for sector I, right, et cetera, right? And then there are these factor loadings, right, that load on the common bits, okay? And, you know, there's going to be stochastic volatility in these taus. There's going to be outliers in the epsilons. You know, we can make these factor loadings, these alphas, right, time vary, you know, as well, right? So those are also going to be random walks, right? So this is a sort of a souped up version of that. It's kind of nice because, you know, at least with these taus, right, being constant, right, you could think about, you know, what's the aggregate inflation that we've been looking at? Well, that's a weighted average of these sectors, right, where the weights are, you know, expenditure weights in all of these different sectors, right? And sure enough, right, if you know, add up a bunch of random walks, you get a random walk, and if you add up a bunch of white noises, you get a white noise, right? So this thing aggregates to the model, right, that we just talked about, right? And so it's got the same underlying time series structure. It's just got sort of more details going on. Okay, so this is what you find if you do that. Okay, I'm not going to walk you through too much of this, right? But this is what you find if you do this, right? I did the same thing. I'm just looking at what I did here. So again, here are these revised inflation data, aggregate inflation data. Here's the real-time data. I'm going to show you the different cheats here that I did. This is the two-sided estimate of tau from this model. This is the one-sided estimate where I cheated and used the two-sided parameter values. This I used one-sided parameter values in data, but I used the revised data. This uses the real-time data and the real-time parameter values. Okay? And remember, you know, what we had before is that these two things looked the same, right? And you kind of nailed it, right? That required knowing the full sample parameter values. If you didn't know the full sample parameter values, it kind of cost you a quarter. If you didn't know the real data, that cost you another quarter, right? And you were kind of out here, right? Right? But you can see here, I think with these, you know, with these multivariate data, I don't know, these kind of things all sort of look the same, right? You've been able to, the real-time data aren't important, and you've somehow adapted to these parameter shifts, right, much more quickly, right, using the sectoral data. So sure enough, if you use the real-time data, what do you see? Well, it's really by the second quarter of 2021, and certainly by the third quarter of 2021, right, using the real-time data, you've nailed this, and you've nailed it roughly, you know, as well as, you know, this tau TT thing. You're going to get a little difference here, right? These are these revision errors, these sort of low-frequency revision errors that occurred in 2022, right? But they're not important for isolating the trend. So the question is, like, what's going on here, right? Why did this, right? Why did this work? Ugh, man, what the heck is this? Oh, yeah, okay. It's, geez. Okay. Now, remember, in the univariate model, in thinking about the parameter values, right, there were like two, right? There's the variance of tau, and there's the variance of epsilon. And then you can put them together and make this theta parameter, this moving average thing. Right, so there was like two parameters, right, that you could easily just summarize by one, theta, right, and that told you about persistence. Okay, now I got this multivariate model, and I got 15 different sectors, and there's all these, you know, 16 different taus and epsilons and time varying alphas and blah, right? How do I think about summarizing persistence for that, right? And here's a little cheat, shortcut, approximation, right? If I think about aggregating, right, these inflations, what am I going to get? I'm going to get a tau aggregate that's this thing. I'm going to get an epsilon aggregate that's that thing. I could think about approximating, right, the variance of this, right, by using the variance, right, of these individual components, right, and right, the variance of this. I guess I've written standard deviations here, right, by combining that. Okay, so what am I going to do? I'm going to take all of these parameters from this bigger model, scrunch them down into these things, right, so we can have something that looks kind of like the univariate model, right, to think about how quickly, right, we learned about persistence, et cetera. Okay, so that's what this does. Also a very busy slide, particularly here. Let's start over here. Okay, so this is, here's the univariate estimate of sigma tau. Here's the multivariate estimate. See, it went up a lot earlier, right, like 2 quarters earlier. Here's the variance of epsilon. Remember the variance of epsilon? The univariate model got very confused, in part because of these revision errors, right, in the early part of the period, right? And when, right, the variance of this idiosyncratic component goes up, right, it's going to keep theta high instead of letting it go low, right? So sure enough, if you look at theta, right, this guy dropped, right, 2 3 quarters earlier. The multivariate version dropped 2 or 3 quarters earlier. So what do you have here? Here's the forecast that comes out of the univariate model. That's this thing in red. Here's the forecast that comes out of the multivariate model. Here's that thing in black, right, the thing in black looks closer to the blue line, right, than the red line. So sure enough, right, you got this thing a couple of quarters earlier, okay? So what is it, right, that makes things work here? Oops. I think this just sort of summarizes everything. Yeah, that's just summarizes everything I just said. Okay, so I'm not going to look at these numbers, okay? So here, this is kind of where we were with the univariate model. You know, here's where we are with the multivariate model. Okay, so why does the multivariate model do better? Well, of course, it looks at more data, right? It can see what's going on in these different sectors, right? If a bunch of them become more persistent all at once, right, it says, sure enough, that's the persistent component instead of the idiosyncratic component. So it's kind of not too surprising that you get that. One thing that I found interesting in looking at this was this little episode right here, right, which has to do with these revised data right here, where the univariate model got quite confused, right, and yet the multivariate model, right, didn't get confused, right? And what's that all about? Well, here's this period, this is my picture for Dean. So this is this revised data right here. Okay, so this is the aggregate inflation, right? Where did these revisions come from, right? These revisions were almost entirely, right, can be explained by what was going on in motor vehicles, right, and motor vehicles and parts. So the real, going in 2020 Q3, which you see right here, right, in real time, this thing said that inflation in motor vehicles was 7%. In fact, it was 18, right? The next quarter, real time was 9. In fact, it was much lower, right, et cetera. So these revision errors were enormous, right, in this period. When the univariate model looked at this, it didn't know that those were revision errors, and it just said, you know, the volatility of this transitory component is increased, right? It put that in, right? What did the multivariate model do? The multivariate model said, there's some crazy stuff going on in motor vehicles. It said those are outliers. It threw them away, right? And hence, you know, it didn't get confused right here, right? That allowed it, right, to change its forecast 2 quarters earlier, right? Really quite remarkable, actually. So that's kind of it, okay? So I don't know. It was useful for me because I had worked on these models, right? Okay, so this is an embarrassing thing. Okay, so I'm going to go back to this. I'm going to go back to a picture here because I have time here. So I will embarrass myself. Okay, so I was given a talk at, I don't know, some conference in the fall about inflation and what the Fed should learn about inflation, right? So the first few of these slides come from that, right? And then I did this calculation, right? This was my cheat where I used the full sample parameter values and the revised data. And I said, the Fed forecasters are just bad, right? I mean, they should, if they'd just done simple time series stuff, they would have done this, right? And then I sat down, right? And then when I was starting to work on this thing, I started saying, well, I should be a bit more careful because I'm in front of a group of forecasters and Dean's going to be here and all of that stuff, right? And then I did all the rest of this, right? And so I was quite wrong when I did it in the fall, that learning about were these shocks persistent or not, which is what the Fed was talking about during this. Are these permanent shocks, right? Are we going to, right? This is whatever team transitory, right? These were sort of all transitory shocks, right? That this model is equally confused, right? Now, it turns out this model, once it started looking at the disaggregated data, right, was less confused, right? It was easier, right, to sort this out, okay? So looking at this, looking at these multivariate data, right, turned out to be useful here. Okay, so I'm gonna stop there.
So we have time for a few questions.
I was just wondering, the seasonality of, you know that the pandemic split up with seasonal pattern, right? That's what VNS was doing, adjusting. So these data, do you use seasonally adjusted data or unadjusted data, or what do you do? These would be the real time. These are the real time seasonally adjusted data and the real time revised seasonally adjusted data. Right? So there's no, and in my model, right, I've got no seasonal patterns. So that's another wrinkle,
Right.
another feature, right, that could be important to add. Because clearly during COVID, whole seasonal patterns changed. We're at home, right? So the question is, I suppose the unknown, how the seasonal pattern changed and how the, what Jonathan said, the echoes of the pandemic, how it's affected the seasonal patterns in the future. You know, that's another thing that I thought maybe thought about it, you know.
So I have not done that. So the
Okay.
question is, right, there was crazy stuff going on in 2020, right, beginning of 2021. That's going to affect the seasonal adjustment in 2022 and 2023.
Right.
Right. So, oops.
Right.
I'm sorry. Thank you. So you know, how is that going to do things?
Thank you. Thank you.
Thanks a lot for the nice talk. I'm very curious, you didn't discuss these bullet points about non-Gaussian.
Yeah.
And now that you've done all this fiddling, I think it's the next next one, right?
Yeah. So this, in real time, you see, you know, here's the volatility, right? Here's the volatility as permanent component. It goes, then it goes, yip, right? But right, and that's because it shifted quite abruptly, right? It took a while for the model to see it, but once it see it, it said, whoa, it went up, right? But somehow when you looked at the statistical model that I wrote down, it said changes like that are going to be very rare, right? Because it's got Gaussian evolution of these shocks. So one needs fat tails, right, in the stochastic volatility innovations.
So then shouldn't you look at it in a probabilistic forecasting framework so that it becomes even more obvious that you need this skewness on some fat tails? Because here you only look at expectations.
I mean,
right?
what I wanted to do were use sort of off-the-shelf models for this. But I think a lesson here going forward, right, if I was working on these models, I would be putting, you know, instead of having sort of Gaussian shocks there, I'd have T shocks or something like that, which would allow, which would make these jumps more obvious, right? Great. Okay. Thank you.
Thank you.
Good. Thanks so much. Thank you.